Pode começar, por favor.
Okay.
Yes.
Thank you, everyone. It's a great pleasure to welcome Professor QI LU, full professor from Sichuan University, to our seminar today. Professor Liu is an internationalized, recognized expert in stochastic control theory and the control theory, of course, with several works in these fields. His work has significantly advanced the fields of controllability, observability estimates, stochastic mass principle, inverse problem, and so on. He is author of several books as well and numerous highlight articles. And he serves as editorial board of top journals like Science, Control and Optimizations, and Science, Annals of Applied Probability. And today is a very pleasure for us to receive you, Professor, and you go forward to his presentation. Thank you very much.
Okay, thank you for the introduction and thank you for the invitation. It's my pleasure, to give a talk here and to keep the stream. I shut down the video. Okay, because
Okay, Professor.
okay, let me first shut down the video and then we continue to. Okay, now, today, I will try to present some recent progress on the optimal control of stochastic partial differential equations. But since the limitation of time, I do not want to focus on the concrete PDEs. I think all of you are expert of control PDEs. You know, in the development of the control PDEs, first people study it in an abstract framework. It's like evolution equation, and then people find for concrete PDE, like for wave, for heat, we need to develop some very sharp tools like the Karma estimate, the micro-local analysis to study that. But for the stochastic PDE, the situation is the same. But today, I do not have time to focus on like stochastic parabolic or stochastic hyperbolic equations. I just want to give you a brief idea that in the stochastic framework, what kind of problems we are interested and what kind of things, what's the difficulty, blah, blah, blah. So I write it in the abstract framework. If for people who are interested for concrete equations, you can see our book or some other papers. You say, for example, for stochastic parabolic equations, of course, we can do better than what we have done in the abstract framework. Okay. Now, let's first recall that, as suggested by Professor Wendell Fleming, there are three milestones of modern control theory. They are Pontryagin maxima principle, Bellman's dynamic programming method, and Kalman's filtering theory and linear quadratic control theory. Today, I will focus on how do we generalize these results for stochastic case. Of course, the original ones are for ordinary differential equations. Then people try to generalize it to partial differential equations, to stochastic differential equations. Today, we say, how do we do that for stochastic PDEs? But before, we first recall what these theories are. First, we recall the Pontryagin maxima principle. It tells us if we have a controlled ODE and we have a set that we call that the admissible control set, which are constituted by all the measurable set functions from the 0T to a separable metric space. And we have a cost functional. Our goal is to minimize that. You say this, of course, we can regard it as an infinite dimensional optimization problem, and we try to use the calculus of variation to solve it. But at that time, punctuation, they introduced a very sharp method to study it. Let me explain how do he do briefly. You say, punctuation says, okay, we follow the idea of the calculus of variation. We do some perturbation. Since the control set U may not be convex, so we cannot consider the convex perturbation of the optimal control. So we use what he called spec variation. It's like this way. And then we compute the difference of the cost functional when there's optimal control and the perturbed control. And one can get the inequality 3, where y epsilon is the solution for the ODE4. One can prove that the L infinity norm of y0 is the same order of epsilon. But unfortunately, we don't know the exact relationship. For example, if we divide both sides of the equality 3 by epsilon and let epsilon tends to 0, usually we don't know the limit. You can have a try if you cannot believe. For example, you know y epsilon is the solution of 4, and you can prove its order is like y is the order is epsilon, but it's very difficult or even impossible to compute the norm of y epsilon over epsilon and take the limit. But then punctuation has an idea. He said, oh, now since we don't know how to compute the limit of 3, then how do we do that? Let's try to introduce another function. It's like an ordinary one, and I observe this very fundamental result. The equality 6 holds. Recall that in our original one, you say all the real ones they appear. Then if we combine 6 and this one, then we can get rid of all the terms concerning y epsilon, and then we can compute the limit. Now the question is how do he find this one? How do he find this one? How do he find the p? You have several ways to do that. Abstractly, you can consider in the functional analysis framework, then p is nothing but the adjoint operator of this one. This another way is you just say you do not care about what's the adjoint operator or blah blah. You just try to find a function p which can help you to get such make this guy and this guy appear. If you want to do this, you will find that p must be a solution of this equation. So you have several ways to find p. Once you have p, then you combine these two, you know, okay, these are the order of epsilon, even you don't know the exact order, but with aid of this guy, we can get rid of them and get the what people call the punctuation maxima principle for ODEs. It tells us what? It tells us if you try to find the minimizer of a function, whose domain may be a very complex set, you can reduce it to find the minimizer of a function, the h. H is defined in the following. You say, this really helps us to simplify the problem. The original problem is an optimization problem in a very complex set. The set U is constituted of all measurable functions, and now it's just simply reduced to find the maximizer of a function. And in many cases, U is like an interval, like a 0, 1, or AB, or U sometimes is a set of finite elements. Then for such kind of one, you really can find the minimizer. Yeah, this is why punctuality maximum principle is very powerful. And there is one point I want to explain is that people may think since H depends on P, and if we do not know P, how do we find the minimizer? Yeah, indeed, let's explain that. To find the maximum value of a function, you must know the coefficients, of course. But if we only need to find the maximizer of a function, you do not really know the exact details of the coefficients. For example, if you have a linear function, y equal to a multiplied with x plus b, to know which point is the maximizer of the function, the information you only need to know is a is positive or negative, right? You needn't to know the exact value of a. This is why punctuality maximum principle works. This is the classical one. And then let's say there are two key steps in establishing the punctuality maximum principle. The first one is people try to do the tighter expansion of the function. No, of course, to do this, you should do several a priori estimate for the solution. This depends on your knowledge of the solution. You need to know which one is the higher order, which guy is small, which guy is large. But all what you need is some techniques of a priori estimate for solutions of the ODEs. The second one is a fundamental observation that you can introduce the ancillary function P to get rid of some guys with the same order of epsilon. Then if people try to generalize the punctuality maximum principle to other control systems, like the PDE, the SDE, or SPDE, you just need to do the two steps. First, you should familiar with these equations. You should know compute what's the J epsilon U epsilon minus JU bar. This is the first. Second is that you should try to find some functions, the P. For the deterministic one, to find the P, we just need to solve an ODE with the final data. But this is, you say, this does not introduce any difficulties, because for an ODE, you give me the initial data or the final data, it's the same for ODE. There's no difference. But if we do that in a stochastic framework, this will really lead to some difficulties. That for a stochastic differential equation, if you give the initial data, that means you want to say how a system evolve under stochastic perturbations. If you give me the final data, that means there is a system which are perturbed by random perturbations, and at last it succeeds to arrive some given destination. You can imagine for the second one, it's really difficult or impossible. This is for long times, people do not know how to define the adjoint systems if you want to do that for stochastic equations. And this was first, this obstacle was overcome by Professor Jean-Michel Bismuth in 1917, and then Professor Pardo and Peng in 1919 introduced the backward stochastic differential equations. Let me explain that. Since now we are work for stochastic systems, so we first introduce some probability setting. For people who are not familiar with this, please don't worry. I just want to explain the idea. I do not take part in the details. Now we have a probability space. Our control, we call that F adapted. For people who are not familiar with stochastic theory, you do not really need to understand what means F adapted. You just consider is like that. We put some constraint on the control. That means when we construct the control, we only can use the information we have observed. That means this guy should be feedback control. Because in the stochastic framework, we cannot predict the future. It's not like the ODE. In the ODE case, indeed, you can predict the future of something, but in the stochastic case, you cannot. So when you use the control, you should use the feedback one. And then mathematically, people use the F adapted, use this, try to use this concept to reflect this one. Okay. Now, our control system is a stochastic differential equation, and when have a cost functional. Here, A, B, F, and H should satisfy suitable conditions, but I don't want to give the details. You just think they are smooth, and you can find the exact details, what kind of A, B, F, H should satisfy in our book. And our goal is still, we want to minimize the cost functional. And we have the optimal control, optimal pair. So if we apply the punctuality maximum principle, what can we get? We do the same. We do the perturbation. You say here, still the formula is the same. The control set may not be a linear space or a convex set. We can only use such kind of perturbation, and we compute the perturbed systems. And the first difference is that in the stochastic case, we should do second order linear expansions to get, in the ODE, recall that. In the ODE, if we compute the difference, we only need to introduce one y epsilon. This guy are the same order of epsilon. But in the stochastic case, besides one epsilon, we still need to introduce z epsilon. Then we can guarantee the residue. Here is a higher order infinitesimal of epsilon. Then to get rid of this guy y epsilon and z epsilon, we have to introduce two equations. These are the equations. And to get rid of them, we should introduce two backward stochastic differential equations. The first one is line. You say here, the equation is that you can understand that P is the solution of this stochastic differential equation, but Q is also the solution. The solution of this equation are constituted by a pair of stochastic process. It's unlike because here we give the final data. If you give the initial data, then the solution is constituted by one stochastic process. But if you give the final data, the solution is constituted by two stochastic processes. This is you can understand this phenomenon in the framework of controllability problem. It's like what? Like we consider a stochastic systems, and you can choose the initial data, you can choose the control, and your goal is to arrive this random variable at time capital T. Then you can prove that if the control exists, it must be unique. So you regard the control as part of the solution. Yeah, you can understand the BSDE in the framework of controllability. Yeah, this guy. And then we need to introduce another one. Remember, we have y epsilon and z epsilon. We want to get rid of both of them. We have, and with the aid of these two guys, yeah, we can prove the punctuality maximum principle. You say here, this guy still, you say this in the stochastic case, the speed rate is the same. We just reduce. Yeah, you try to find the minimizer of a functional to you find the maximizer of a function. Yeah, this really help us to find the control. The difference is that in the stochastic framework, we have this guy is the counterpart of the deterministic one, the Hamiltonian, and we have the red part. These red part are new. The red part are they appear just because of the stochastic case. You can understand this as what this as risk. Yeah, if you consider the stochastic control problems as a company who want to invest, do invest, they want to earn money from the stock, then they should not only try to maximize their profit, but also try to minimize the risk. So then this is why in the stochastic case, we cannot say, okay, oh, I want to a very large profit, but of course, in this case, maybe the risk is also very big. So for smart guys, what he should do is try to maximize the profit and try to minimize the risk. And then the stochastic maximum principle told you what you should do is try to maximize this function. Yeah, this is the stochastic one. This is for SDE. And there are two lecture generalizations. Yeah, you can imagine this result is very good, but then what can we do in the next? First is that in the proof, they assume F must be the natural filtration of W. This means what? This means all the unknowns, all the random perturbations comes from the Brown motion. There are no other uncertainty in the systems. This is, frankly speaking, this is not many cases do not fulfill this. And the second one is we are most interested in that these results are for stochastic differential equations. Yeah, how do we do that for stochastic PDEs? To do that, we meet two main difficulties. First is that for the filtration, yeah, how do we solve the BSD? Because in the classical result, like by Pardo, Peng, and Professor Ben-Susan, yeah, for all these guys, when they study the backward one, the BSD, a key tool is they call the martingale representation theorem. This theorem only holds when the filtration is generated by the Brown motion. That means all the uncertainties are coming from the Brown motion. There is no other uncertainties in the market. This second one is even worse. It's what? Remember, we said in the stochastic case, we have y epsilon and z epsilon. Then we need to introduce two equations to get rid of them. The first one is backward the stochastic differential equations in Rn. The second one is a matrix valued BSD. in finite dimensional case, like you told me a solution is Rn valued or matrix valued. Indeed, they are the same. Because for any matrix, you can always regard it as a vector in some Rm. M, for example, here m equal to n squared. But in the infinite dimensional case, yeah, this does not works, because when you generally you cannot regard an infinite dimensional matrix as an element in some Hilbert space, right? Yeah. So in the infinite dimensional case, we cannot simply regard a matrix as an element in a Hilbert space there. And unfortunately, there's no stochastic integration theory to study how do we define the stochastic integrations for a Banach space valued stochastic process. Here, I mean there exists no. I do not mean there may be someone and we do not find it. We mean there's no. Indeed, people have proved that there's no stochastic integration theory for Banach space constituted by all the bounded linear operators. Yeah, this has already been done. So even I do not explain what's the mathematical meaning of stochastic differential equation or backward stochastic differential equation. Yeah, you can imagine that. Yeah, what we said is what indeed it's in to study such kind of equations. The first step is we have a theory of stochastic integration, but now in the infinite dimensional case, it's already low. It's impossible for us to have such kind of integration theory. What can we do? Here we introduce the so-called stochastic transposition theory to overcome these difficulties. Let's explain that. Now we first explain how do we overcome the difficulty that the filtration is not the natural one generated by the Brown motion. We do in the following way. Now, remember, our difficulty is that how do we define a solution of an equation? Yeah, you say, okay, for a solution of an equation, we have many ways for differential equation. Yeah, we have strong solution, weak solution, or yeah, mild solution. We have lots of ways. But here we know all of them do not work. Then what should we do define the solution? Then we remember why we should introduce such kind of equations, because we want to get rid of some terms when we compute the difference between the cost functionals. We have some terms we cannot get rid of them. Then we say, oh, we just do some trick. We introduce some ancillary function. We use this function to get rid of them. So in the ODE case or SVE case, just because we are very lucky, we say the ancillary function we introduced, they are solution of some ODE or BSD. Here, so if we want to define the solution, we just say what kind of functions or stochastic process can help us to get rid of these terms. Yeah. Okay, skip here. Here is the framework. Yeah. First, like for example, for the equation 15, What kind of pairs y and capital Y can be the solution of the equation 15 if we do not have the martingale representation theorem? We can do like this. We introduce the equation 17, and we know if this y and capital Y can help us to get rid of the extra terms in the difference of the function laws, then it must fulfill this guy, fulfill these equalities. Or in other words, what we really need is a pair of stochastic process such that for any psi 1, psi 2, and eta, this equality holds. Yeah. So we simply use this guy as the definition of the solution for the backward equations. And if it admits some classical weak solution, then we know this really holds. If it does not admit the classical solutions, if this holds, it's enough for us to get rid of the extra terms. So in such a situation, we use this to define the solution. And we can prove it really has a solution. Yeah, it's well posed. Yeah, this is the first step. We find a way to overcome the obstacles that we cannot use the martingale representation theorem. The key proof is some Ritz type representation theorem. Yeah, that means we generalize the Ritz type representation theorem for Banach space constituted by stochastic process. The second one is some like the big differential theorem, but for stochastic process, and some Dubus theory. And the second one is that now, as we said, there is no suitable integration theory for operator valued process. Yeah. What should we define the solution of 20? The same. Yeah, we say, oh, now there's no stochastic integration theory. We cannot define 20 in the classical way. Then, yeah, what should we do? We just say why we should the P, because we want to get rid of some extra terms. Then what kind of properties P satisfied? Then we can find the solutions. It's like this. We introduce the equation 21 and 22, and we find that, here I skip, if the following inequality holds, then it can be used to get rid of the extra terms and help us to establish the punctuation maximum principle. Yeah, this is the observation. And of course, if this inequality holds and all these are true, then we will know we should add some integrable conditions or some continuous conditions on all these P or these Q to make this equality, to guarantee this equality makes sense. And to do that, we introduce these sets. Yeah, these sets are nothing but just the sets of some stochastic process such that this inequality makes sense. Yeah. And we find, fortunately, it really has solutions for in this way. You say, if when we try to define something, if we don't know what kind of definition we should introduce, we just ask ourselves, what's your goal? What's the goal of introduce such definition? Yes, and we just use this to be the definition of the concept. Of course, by this way, once we prove there really exists such kind of things, we can use it. But then the difficulty is why such kind of things exist. The proof is very complex. I can not explain the ideas here, but you can find it in our book. I will give the reference at the end of the talk. And now I show you the maximum principle is like this way. It's the same. You say, although it looks very complex, but the spirit is the same. It tells you if you want to find the minimizer of a functional, you just need to find the maximizer of a function. You say, yeah, for the functional, the domain is very complex, but for the function, the domain is usually very simple. And in many cases, it's only considered like by 2 points. When, for example, when you study the bound control, it's indeed it's only constituted like 0 and 1. You can simply find which guy is the maximizer, and then you can construct the control. Now, we turn to the dynamical programming principle, and the same. I first explain what's the ODE case, and then I explain what we have done for stochastic PDEs. You say the key point for dynamical programming is to introduce a family of auxiliary optimal control problems. Our original control problems is the initial time is t equal to 0, and the initial data is like x 0 equal to some point, and then Berman said we can introduce a family of optimal control problems, like the initial time is s and the initial state is something y. Then we can consider the cost functional is from s to t. Of course, you say we get a family of optimal control problems. All the problems have the same structure with our original one. Why do we introduce this? Because with the aid of these auxiliary optimal control problems, we can introduce the so-called value function. And we have the following. People call that Berman's principle of optimality. That means the global minimizer must be local minimizer. This is nothing. This is just to tell you. If you have a way from S, the global minimizer must be local minimizer. Yes. With this, we can, if V is smooth, we can find the PDE satisfied by V. It's in the following way. You say this is the first order PDE. And if we are lucky enough, if we can solve this PDE to find the way, then fortunately, we can construct the optimal feedback control in the following way. You say now, since we know what is V, so in this H, what we do not know is only U here. And then for a fixed T and X, we can find the maximizer of this H. And then we get a function depends on both T and X. And we claim this guy is optimal control and it's in the feedback form because it's like this way. This is if we are lucky and if V is smooth. The proof is very easy. We just compute the derivative, we get this one, and we will find this inequality. Remember, the definition of this guy is the infimum of the functional. Now, if we succeed find a function, we take it into the functional and we attain the infimum of the functional. That means the function we find is the minimizer of the function, right? So, Berman's principle, if in a word, it's like this. First, you form the PDE to get the value function. Second, you find the optimal feedback control by finding the minimizer of a function. And then, yeah, we get the optimal control. Particularly, it's in a feedback form. Yes. However, I believe all of you are low. Both the two steps are not very easy, particularly for the first step. First, how do we find a solution of a nonlinear PDE? Second is why this solution is C1. Yeah, you say for a nonlinear PDE, generally speaking, yeah, you cannot expect a C1 solution. Then this, yeah, to overcome this, the professor, yeah, Crandall and Lyons introduced the concept of viscosity solution, and then they employ some non-smooth analysis to try to construct the optimal feedback control. The spirit is like the step one, step two, but generally here, yeah, we only get the viscosity solution. It's some Lipschitz function, but not C1. And here we need to use some measurable selection theory, yeah, very complex theory. But the idea is like here. Yeah, here today I do not want to explain, yeah, the viscosity case. I just want to explain we can do that for stochastic PDEs, the same procedure. Consider a controlled stochastic PDE. Here A generates a C0 semigroup. And we want to minimize this guy. Here is the assumption, just forget it, some continuous assumptions. Yeah, nothing. And we introduce first a family of optimal control polynomials. The idea is the same, you say, and then we define the value function like here. You say like here. And now, first, we need to prove this guy. The proof of 42 is much more complex than the one for the ODE case. For the ODE case, if we want to prove the global minimizer is a local minimizer, yeah, the Bellman's principle, indeed. This can be done like, I think, in half a page. In half of a page, you can prove 29. But in the stochastic case, this is really very difficult to prove this one. The reason is that, yeah, in the stochastic framework, if you want to, yeah, the main problem is once you take this guy, yeah, and the original one, it's not very easy for you to find the connection between these two things. It's not like in the deterministic case. In the stochastic case, people introduce, usually there are two techniques to do that. First, like done by professor like Wendell Fleming, Meter Sonner, maybe you know that. They introduce the framework of relaxed control. Yeah, they do relaxed control and they prove this, use that technique. The another one is based on the theory of backward stochastic differential equations. And here we follow the second one. We prove this guy, and I will show the conference, but due to the limitation of time, I do not try to explain that. And then, if the same, if V is smooth, then we will find the PDE satisfied by V. Here you say the V first is a function because sorry, here should be multiply. V is a function of two variables. The first one is the time variable. Second one is the space variable. But here the space is the spatial variable. Here is not some Rn, like the ODE case. ODE case here is Rn. N is the dimension of the equations. But here the space is H. That means 49 is a PDE for functionals. Or in other words, since H is a separable Hilbert space, you can regard it as L2, like the L2. So this can be regarded as a partial differential equations, but with infinite many variables, right? It's not a PDE on Rn, PDE on H. How to solve 49? This is very difficult. It's indeed, in the study of PDEs, we always you say in the modern framework, it's important to have the integral. We always like to do energy estimate or do some other estimate. What we have introduced the Sobolev space, but to do that, the first is that we should have an integral theory. We should the first step to construct the Sobolev space is we have LP space. And to have LP space, we should say, depends on we know how to do the big integral in a subset of Rn, right? But now we are in an infinite dimensional space. There's no the big integral. There's even no the big measure on such kind of space. So to study the equation 43, this is really very difficult part. And it's difficult. And I explained today, I do not want to think how do we solve 43, and I will show you some conference, but I explained once we get away, what can we do? We can prove what we call verification theorem, and this theorem help us to find the optimal control. You say this says that. This says if first, because we may not be continuous or smooth, so we just consider its generalized derivative, and if we can find a control such that these four equality holds, then this control is the optimal one. This means please do not focus on the details. They looks very complex, but they are indeed they are natural. You just remember that once we can find a way, we can find the optimal control, and the way comes from what? Way comes from our definition of the family of optimal control. Or in a word, if you are not familiar with dynamical programming, you just remember that, the key tools is the value function. Once we get the value function, we find a way to construct the optimal control. But of course, the value function for different control systems, maybe they are very difficult or but anyway, the idea is like this. And in stochastic framework, we have already done this. We know, okay, there's and of course here you say I put two in red and another in blue. The two in the three blue ones, that means this natural one. You say here is just a definition of G, and both 47 and 48 they are natural. But here the red one, this red one are not very easy to fulfill. You say the first one is what? The first one tell you the state in some smooth space. You say A is the generator of the operator semigroup. Yeah, that means first this holds. The second is that some Lipschitz continuous of the value function. For this one, we can prove if A generates an analytic semigroup, it holds. An example is that for stochastic parabolic equations, this holds. The second one, this means some regularity of the solutions. We can also prove that for stochastic parabolic equation, 45 holds. So at least this theory told us, yeah, we can apply it to stochastic parabolic equations to get the optimal control. And for like other equations like stochastic hyperbolic equations, we don't know how to do that. Okay, here is just the theorem. That means you say this theorem guarantees that once A generates an analytic semigroup, then the condition holds. Yes. Okay. At last, I have 5 minutes. 5 minutes, I think I explain, yeah, very briefly the linear quadratic control theory. Just remember, I say 3 milestones. Punctuality maxima principle, I have just explained that the dynamical programming is done for some special case. For punctuality maxima principle, our result covers all the usual stochastic PDEs. For for dynamical programming until now, our result only works for stochastic parabolic equations. And now we say what happened for linear quadratic control problems. For why we call that linear quadratic, that means the control system is linear and the cost function is quadratic. This is almost the most simple long-travel optimal control problems. You say if the control system cannot be simpler, now it's already linear control system. The simpler one is what? The second is that the cost function cannot be simpler. Now it's quadratic one. The simpler one is the linear one. For linear one, yeah, it's very easy to find the optimal control. So this guy is the most optimal, I think simplest long travel optimal control problems. But why we should study it? It seems that one can apply the punctuality maximum principle or one can apply the dynamical programming to solve it. But why? Why we should focus on it? It looks like a simple case of the systems we introduced at the beginning. The reason is that for this equation, we can really find the optimal feedback control. You say if you apply the punctuality maximum principle, the optimal control you get is like the given by 58, right? You say, oh, this seems good because to get 58, you only need to know what is P bar. But to get low P bar, you only need to solve 57, right? Yeah, this looks very perfect. This is nothing but an application of the punctuality maximum principle. But unfortunately, the control we obtain may be unstable under small perturbations. For example, we consider the following toy model. Yeah, it's like this way. For this, we can really solve the equation to find the optimal control. The optimal control is this one. But now, suppose there is some major errors. We think the initial data is 1, but the really initial data is like 1 plus epsilon. For any epsilon not equal to 0, if you take your optimal control inside, the really initial data is 1 plus 0, but you don't know due to the the error in the measurement, you think it's 1, then you compute, you get this control, and then you take it into the control system, you will find the cost function will equal to infinity. On the other hand, if you take the control u equal minus x, you will find for any initial data, this guy will be an optimal control. Yeah, this is tell us why we like optimal feedback control. Now, how do we do that for general LQ problems? Yeah, because you see the equation. This is a linear equation. The dependence of P and X should be linear. So Kalman assume the linear relationship are given in the following way. And then if 60 holds, then we know the optimal control is in the feedback form, optimal feedback form. And we will find if 60 holds, if and only if P is a solution of the following Riccati equation. And in some natural conditions, we can prove the Riccati equation is well posed. This is the first done by Professor Rudolf Kalman. And then we know to find the optimal feedback control, what we should do is to solve a Riccati equation. And what happened in this for stochastic PDEs? For stochastic PDE, like in this way, yeah, with this guy, and then now A, B, C, D are operators. And the cost functional. Our goal is to find the optimal control in the feedback form. So we first introduce this definition. And this space, please just ignore that. It looks very complex. It just some special operator valued space such that this equation is well posed. Yeah. And to find the optimal feedback control, we have to study such kind of equations. This is an operator valued backward the Riccati equation. Yeah. Remember that we don't know how to define the stochastic integration. So how do we study the well-posed list of this guy? We still use the transposition solution. That means we seek for P and the lambda such that this equality holds. And we can prove there exists an optimal feedback control if and only if the Riccati equation admits a transposition solution. Yes. And here is the reference. The first one is a book, around 60 pages. We try to explain all these things. The second one is a survey paper. It's more readable than the book. And the third one is the paper to study the linear quadratic control problems. The third one and the sixth one. Indeed, and the fourth one and the fifth one are study the dynamical programming principle. This guy, first and two, contain the punctuality maximum principle. Okay, I think I stop here. Thank you.
Thank you, Professor Lu. Well, let's open. We have time for 2 questions or comments. The microphone is open. Everyone can ask Professor Liu. I have just a curiosity. I know This kind of machines work very well for parabolic and hyperbolic problems, including in finite dimensional case. What's happened? Do you know some results for this specific equation, like for example KdV or so on?
Thank you. For the contractive maxima principle for KdV is done, and for the problem is for the dynamical programming. Now we don't know how to do that for KdV because the KdV we have local smoothing. They cancel the smoothing effect, but we don't have the global one and the regularity that we our assumption on the regularity of the state equation. Yeah, it's not enough for apply the dynamical programming, but I believe it should be done or it can be done. But I just say our technique now does not work.
Okay. I see. Yes. Okay. Nice. Some another questions or comments? If not, let's thanks Professor Liu again. Thank you, Professor, for this
Thank
nice
you.
talk.
Thank you very much.